So nice to see you. Yeah, and of course, it's a pleasure for us today to have Ondra here, who will tell us about Ritchie flat metrics from GLSMs with Shadow.
Thank you.
Okay, thank you, Ondra.
So, I'd like to start with thanking the organizers for organizing this wonderful conference and inviting me to speak. It's a pleasure to be here. And okay, so I will report on this on the paper, which will hopefully come out soon in upcoming weeks, with these wonderful collaborators who are listed down there, not in alphabetic order for some reason. I don't know why. Okay, I'm realizing that it's probably outside of the scope of this conference, although when I was thinking deeply about it, there's at least some deformations and some dualities. So no integrability today, but at least I'm checking 2 boxes out of 3. And it goes without saying that you should ask questions as I go through it. If you don't understand something, I have a tablet here so I can write some extra stuff in my presentation. But okay, so what is the motivation for this work? Basically, so I don't have to motivate for you that Calabi-Yau manifolds are interesting set of manifolds we study in physics for compactifications of string theory. But and probably also know that despite having abstract proofs, rarely we have examples of Calabi-Yau or Ritchie flat metrics in for some interesting geometries. There is a nice construction for getting some metric on Calabi-Yaus, which is coming from the gauge linear sigma models. But that rarely, this construction gives you some metric, but rarely gives you Ritchie flat metric, almost never, to my best knowledge. And so what we studied in this work is sort of extension of this construction of a quotient coming from GLSM, which indeed gives you Ritchie flat metric on the nodes, and both in the singular limit and resolved case. I will explain what that means if people don't know. And this might sound exciting. I should preface that it's for now it's a small family of examples. Most of them are already known through other means, but we're hoping that it's sort of constructive procedure which can be extended further to maybe less known situations and provide new methods and new ways to obtain these Ritchie flat metrics. Okay, so that's the motivation. I should maybe, I put here a calculation to, I don't know, to whet your appetite, and maybe it doesn't says anything to you, but I just wanted to show you that if you know the techniques of GLSM, probably you've heard about conifold. If you know that conifold has a Ritchie flat metric, right? But because it's a Calabi-Yau. But if you perform a standard GLSM construction, you will end up with this scalar potential. I will explain what scalar potential is and everything in the talk. But if you calculate the metric out of it, which is basically a Hessian of this function, which is not really a function, then you'll find some metric which is not Ritchie flat, and I'll teach you a way how to, I don't know, tweak the construction such that you get something that's Ritchie flat in the end. So okay, so with that said, I will move the outline of the talk. There's plenty of things to cover, but they sort of fit into these 5 general boxes. First one is I'll just review a bit of a 2D sigma model technology, nonlinear sigma models, GLSM, and how do they look in 2,2 supersymmetric extension. Then, since that's a natural language for models we're trying to study, I will give you a lightning course in toric geometry and explain how these target space geometries are encoded geometrically. And okay, so there's a bunch of things you need to understand there. Keller quotient, what are the resolution or Keller parameters or FI terms, and I'll try to, I don't know, hopefully give you some quick working knowledge of that if you haven't come across these things. Then I'll move to this Legendre transform part, which is just a technical tool to help us to actually effectively calculate as to whether these proposed Ansätze are Ricci flat or not. And then, okay, the main protagonist is this shadow field construction, which will be at the very end, which is some very minimal extension of standard GLSM, which will allow to perform a Ricci flat quotient. So, and then I'll comment on what class of examples we can we understand for now. How can we smooth out things, roll of FI parameters, and so on. So I will stop here if people have any questions before I dive into the first topic. But seems like there's nothing for now. All right, so I'll start nice and easy. Nonlinear sigma models and GLSM. Oh, wait. And yeah, okay. I forgot the old title. So now no supersymmetry for now. Sigma model is just whatever two-dimensional, doesn't have to be two-dimensional, but in what I'm gonna talk about, two-dimensional Lagrangian on these maps from Riemann surface to some target space. Target space can have some extra structure, metric, symplectic form, complex structure, as we'll see later. And then, you know, basically, when we're talking about the pure bosonic case, whatever goes, I wrote something pretty standard here, kinetic term, which is a metric, right? So that's the metric from the target pulled back to the worldsheet, and some function which is in which is just added there, which is also a function pulled back from the target. This is in general very complicated thing because these metrics could depend on the field, so they're nonlinear models, and unless something special happens, we don't really have a good grasp on these. Okay, however, some of these models, some of these metrics, if you will, can be recast into something slightly more manageable, which is called gauge linear sigma model. And the idea is probably something you're all very familiar with, as I've seen in the course of this week, and that is that we can realize these complicated metrics as metrics obtained from the quotient. So we're working in some bigger space. So now I have a different metric, this big metric G, which is flat. Doesn't have to be flat, but I want to start with something easy. And then we can gauge some isometries in the target space. We do it by introducing covariant derivatives with these fields A. There could be more of them also, as we'll see later on. And then we can perform the quotient, i.e. we will integrate out the field A, and what we'll end up with is some nonlinear sigma model with special class of metrics. Not every nonlinear sigma model admits such a description, but the ones we will study do. And that's the main tool we will be using. So just, you know, for people who might not be familiar with this construction, for the CPN model, we've seen also this week that admits GLSM description, and it's very easy. It would be you would start with n+1 free fields. You would give them all charge 1, and you would gauge accordingly. And then if you integrate out field A here, you would end up with nonlinear sigma model on the quotient with a famous metric, Fubini study metric. So that's a way to get to one of the nonlinear sigma models of interest. Okay, so that's you probably know all of that. I should say, okay, I could have in principle gauged whatever isometry, abelian or non-abelian, but because things are much simpler in abelian case, and it already gives you a huge family of examples, I will stick with abelian models, but I will be gauging just abelian isometries, although maybe more of them. And so things simplify and get some nice combinatorial description. So why is that? We'll have these fields phi, which are spanning the embedding space, if you will, some bigger space. And then the gauge fields, which are corresponding to these isometries, C star or U1, based on whether you prefer thinking as in terms of symplectic quotient or GID. Well, since these are abelian groups, you can diagonalize the action on the field, and all the information I need to give you for you to do the quotient is just bunch of charges, these QIA, these guys. Okay, they are telling you how is ith field charged under jth C star action. So in order to package this model nicely, I basically just need to give you this one matrix of charges. It's a matrix which has one row per each C star action and one column for each field. Okay, and in literature, this matrix Q is known as charge matrix. Okay, all right. So again, an example. If you are familiar with A2 singularity with Duval surface, you can write a GLSM description for that with such charge matrix. And you see that from these sets of charges, you can read off the kinetic term. So you see the field, first field is the first column that tells me that it's only charged under the first isometry. So there's only A1 appearing in this bracket. In the second one, I see that it's of charge -2 and 1. So that's this one and that one and so on. So that's how the abelian quotient works and how it's encoded in the charge matrix. All right. Okay, so there was still bosonic, still nothing interesting. Well, I mean, it's already fun to play with it, but now some extra structure. So while the uplift of the bosonic model to 1,1 superspace has no obstruction except for having spin structure on your world sheet, the 2,2 extension is already restricting the target space quite a bit. Namely, it requires the target to be Keller, or in general, generalized Keller, but I will not talk about those examples, although that's also interesting family of models. So what is the Keller manifold? It's a complex manifold, so it has a complex structure. It has disclosed symplectic form, which is locally generated by a function, well, not function, but a section of some bundle, which we'll call Keller potential. And then these two structures play nicely together, and they make up metric, right? If you put the complex structure in the first slot of symplectic form. So that's the Keller manifold, and if you have that kind of data, you can pass to the 2,2 superspace description of such models, and many things will just be very pretty in the description. However, as you might know from 4D-1 supersymmetry, maybe that's more familiar to people, these fields, the superfields, which are unrestricted, they are way too large. They have way too many fields in the multiplet, and they're not reducible, and you need to impose some constraints in order to cut out the right amount of degrees of freedom in your fields. And although there's way more fields than I'm listing here, I will just work with these chiral and twisted chiral fields. So chiral fields are something like holomorphic coordinates on your manifold, roughly, in a sense that they are killed by the d-bar superderivatives. And you should think every time I say chiral, although it's not applicable in general for generalized Keller manifolds, it's slightly different, but in the examples I will talk about, chiral means matter every time, or just regular coordinates. While there will be also twisted chiral fields, and you should think of those as something encoding gauge fields. Okay, so chiral are matter and twisted chiral have curvature in them. Okay, these are something you don't know from 4D-1, right? They don't have an uplift for. So if you want to find this, if you want to find a multiplet with a potential instead, which we all need for gauging, you need to work with this real field, which is like a potential. So think of this as an analog of F is equal to dA. So F is like sigma and A is like V, roughly. And V indeed has a connection in there, some extra auxiliary field D, and fermions lambda. All right, so okay, so that's that. Okay, perfect. Okay, so what's so nice about these 2,2 models? First, non-linear sigma models. If you go a couple slides back, you could have written many things in those models. Well, here stuff is very restricted. Roughly, there's two terms you can write down. You can write down these D terms and F terms, where you integrate over the whole space or chiral half. And there's just two functions you need to specify. Here is some general function, again, which is not a function. There's some gauge symmetry to it. And then there is this holomorphic function, which is called F term. This K turns out to be exactly matching the Kähler potential from the local description of the Kähler geometry I talked about. F terms are more like cutting out some loci inside your embedding space, and things are more interesting with them, but also way harder than without F terms. And for that reason, I will from now on set W to 0 for everything what will come next. So much less interesting class of examples, unfortunately. Okay, so that's that. Now, how are these 2,2 GLSM? So they, as I said before, in the bosonic case, you start with some flat space. So you would have a Lagrangian of this kind, where you have just sum over quadratic contributions, bunch of chiral fields, and then you perform gauging, which is just done in 2,2 language by inserting these exponentials made out of the V's, which are the real superfields carrying the gauge field in them. So it's very similar again if you're familiar with for the Unique 1 technology. So this is the way gauging works, and then if you go down to components, you can see that the first part looks exactly like the bosonic, and then it gets nicely enhanced to something supersymmetric. There's a term which will play a role later, which will be linear in gauge field, and it will be accompanied with a number psi. This number could be in general complex, and it's called phi-Oikos term. The real part of it will play a crucial role later for smoothing of the metrics. Okay.
Question: How
Yeah.
does V transform under gauge transformation?
It transforms with a shift of chiral and anti-chiral field. So it's a
So is this gauge in there?
It is, yeah. But you cannot, for instance, you cannot write Fi when you have a, so this is all abelian. If you go non-abelian, you cannot have anything like that. And you cannot have this Fi term except for the Cartan, but yeah.
Okay.
Yeah.
Is there in 4D one, in order for that to make sense and be compact, one has to go to a particular gauge, the Sumino gauge?
Yes.
In here, is there something similar, or the number of fields makes it nicely to go with?
No, you also have something like that. Yeah. Mm-hmm. Yes. Okay. Thank you for the questions. Now I'll already preface the main technology, even though it might seem very mild. Difference from the standard GLSM. So you see, the starting point was this metric on the embedding space, which was positive definite, right? There's pluses in front of all these squares of phi's. While it will turn out that if you relax that, if you let some directions to be negative definite, things will be much prettier. But more about that later. That's the main technique. Just let me say that I will call these positive directions. Well, those will be just normal fields, and the negative ones will be the D shadow field. So for now, shadow field is nothing spooky. It's just negative direction in the embedding space.
Then these are kinetic terms, right?
Yes.
So is to put in the wrong sign kinetic term?
That's right, which might seem alarming, but the point is that even though the embedding space is not positive definite, the quotients will be the way we will take them. So the final geometry will be fine. Yeah, it will be just a trick. Yeah. Right. So again, if you want to rewrite this A2, this Duval singularity, as I showed you before, this would be the set of kinetic terms, and there would be a Fi term for each of the gauge fields. So there were two gauge fields. Now we have two Fi parameters. All right. Okay, I should say this is again a bit restricted. This is a general GLSM you can write down. The kinetic term is what we have. You can add a kinetic term for the gauge fields as well, but we will not have those in our description. This is the standard F term from before. We don't have that either, and this twisted F term, this W tilde, that can be also more general, but we only consider it linear in the gauge field, which is the the Fi term. That's where the Fi term is. Okay. Yeah, I already said that this Fi has a real and imaginary part. All right, and one last thing to know about this model is that once you go through arduous process of going to components from that supersymmetric description, you will identify such potential for the field, and you can forget about most terms. There's more terms also, which depend on W and so on. But what is crucial is that there will be this guy in here, which exactly you see that it depends on the auxiliary field of the vector, and then it multiplies this strange real function made out of weighted sizes of the chiral fields minus the Fi term. So this will play a role later in the symplectic quotient. That's the moment map for people who know. So you see that it appears naturally in the 2,2 GLSM model. So, and by integrating out dA, you will impose the moment map to be 0 or to be equal to psi more concretely. And that's how the quotient is realized in physics. All right, so now I will step back a little and I will describe some mathematical background for how to encode these models in pretty pictures. Okay, but maybe should I can talk and see if people, yes.
Can I then pass it? We can discuss it later. So usually in 4D, you take two n equals 1s, you put them together, you fix some coupling, and it's n equals 2.
Yes.
But in here, you had an extra condition, right? So instead of, you can take two 1,1 models, you put them together, and it's not 2,2. You need, where is the dynamics of that extra condition coming?
But I think in 2,2, if you think of a target of the scalars, it also needs to have some kind of special geometry structure. So there's also some geometric condition which is coming into the
you mentioned.
Yeah. Yeah.
Right.
Thank you. Okay, so toric varieties, they will be basically these vacuum manifolds of the models I'm interested in. They are just abelian quotients of C star n. And really, like there's a huge literature on toric geometry, but what you should know, for at least for purposes of this talk, it's basically a n-dimensional toric variety is a complex manifold, which is basically C star to the n plus some points. Okay, that's the logic. So it's like a algebraic torus plus extra compactifications in certain points. What do I mean by that? So for instance, if I list all the one-dimensional examples, there's just 3. There's a C star, which is basically a tube, right? There's a C, which is a tube where you add one point, and there's a CP1, or aka S2, where you add 2 points. So that's what I mean by this vague description of toric geometry. It's either compactified nowhere or in one end or two ends. Okay, and all the other ones generalize. So you can imagine that in higher D, there's just more ways to add these extra points or not. And many famous examples admit such description. CPN is one of them. Duval singularities, conifold, suspended pinch point, you name it. There's plenty of examples people care about. Okay, so all of this is nicely captured by some pictures I will try to explain now, which are called fans. And again, like there's a lot of theory you can say about this, but roughly it's a picture which has these generating vectors in there. And what you can gather from these pictures, if I give you a picture, you can just take the coordinates of those vectors, those spanning vectors, and put them in the rows of the P matrix. So you see here I have this A1, it has these generating vectors, right? This is the first one, second one, and so on. CP2 has following picture. I'm not saying why is it corresponding to that, but that will hopefully follow in a bit. And conifold has these 4 generators. So you see, there's more generators. I can tell you right now that the dimension of the toric variety will be dimension of this embedding space, the space where the arrows are living. So these two will be 2-dimensional, right? If you know CP2, you know that it's 2-dimensional. Well, the third one is in 3-dimensional space, so it will be 3-dimensional manifold. So, but you see that I have more vectors than the dimension of the space. Okay, this one is maybe confusing, right? Because it looks like 3-dimensional, but I'm really thinking of this vector as pointing in the -1 direction. But so I have more vectors, and so there's conditions among them. They're linearly dependent. And what is taking care of what is encoding that linear dependence is exactly the charge matrix you've seen before. So basically, all these matrices, they don't have to, but if they have a kernel, it's encoded in this Q matrix, and that's the charge matrix we have extracted from the abelian quotient GLSM model. More vectors you have, so if you have more than 2 in 2-dimensional picture, you will have more lines in the Q matrix. Okay, so I don't know, I gave another example here, which has 2 rows of the Q matrix. Okay, so you can go back and forth. If you read off Q, you can construct P. They're not unique. There's some preferred basis based on integrality, but I don't have time to go into that. But in principle, you can go from Q and P description back and forth. Okay, so what is the dictionary with forgetting about math? What is the dictionary with the GLSM models? Roughly every row of this P, right? So every arrow in my picture corresponds to a chiral field, and every row of Q matrix is one of the relations among the vectors, which will correspond eventually to the gauge field V. And for each of these V's, you will have one Fi term. So that's the name of the game. Okay, there's some toric geometries are prettier than others, at least for physicists, and those are the ones giving rise to Calabi-Yau quotients. So the condition is that, so what I want? I want to have some nifty condition which tells me when I perform a quotient as to whether this variety I ended up with is Calabi-Yau or not. It's very easily obtainable from looking at the charge matrix and just summing the rows. And if the sum of each individual row is 0, then rest assured the quotient will be Calabi-Yau variety. There is also a reason, purely GLSM reason why this condition pops out, but geometrically it's that. One imprint of that, if you look at your fan, if the arrows nicely align along some hyperplane, so their ends sit on the hyperplane, that's the geometric imprint of that Calabi-Yau condition. So this one is Calabi-Yau, it's a two-dimensional Calabi-Yau, but still. This one is not, because they're pointing in all sorts of directions. Conifold is Calabi-Yau because it's sitting on this nice hyperplane in Z1. All right. It's really nothing, I don't know, surprising. It's just that you can take a, Calabi-Yau is just scalar with holomorphic non-vanishing volume form, and if this Q is if this condition on Q's is satisfied, then you can just inherit holomorphic volume form from this embedding space. I can explain that to people, but maybe I'll skip it for now. All right, so there's a dual. Hopefully it's clear that if I give you a picture now, you can read of the P and you can read of the Q, and then you can write down the GLSM model. So that's the construction. Now there's a nice description which is sort of dual to that, and which will be prominent in a little bit, which is description via Delzan polytopes. And basically, if you take your fan, you can if you think of each of these generators as normals to the planes, you can go to a dual space and write these planes which are intersecting and get some sort of polytope. So by polytope I mean I just look at the like a positive side cut out by these planes. What is the straight up advantage of this description is that you can immediately see geometrically a role of Fi terms, and because before there was really no way to encode that in the fan. Here in the dual picture, the relative position of these planes are controlled by the Fi terms. So if I turn off the Fi term, this is A1 again. If I turn off the one Fi term I have, all these planes would nicely meet at one point at the origin. Otherwise, the second one is pushed to the bulk. There's another geometric thing you can see, and that is that if this polytope cut out by stuff is compact, then the geometry will be compact. If it's not, then it's not. So A1 is not compact. You see, it's this huge non-compact polytope. All right. So, and how would I again concretely get this picture? Well, if I give you CP2, for instance, this is the set of generating vectors. Now we can write these planes out of it. You just multiply here by some mu1, mu2, two variables, which are basically the variables of this space. And then you can set them to 0, and that will give you some hyperplanes. And then if you see that these hyperplanes, they exactly satisfy that condition as the vectors do. Not surprisingly, they sum to 0. But you can deform them. You can add to each one of those your psi, and then they sum to psi, and that will be exactly moving one of those planes in the bulk. So that's the geometric imprint of deformation. All right. So now the quotient, right? The quotient is basically just something you know from Hamiltonian mechanics. That if you have a action of some group on some manifold which is equipped with Poisson structure, which Cn naturally is, you can just hook up the homomorphic and anti-homomorphic guys together. Then for each of those generators, for these vectors, there is a moment map, and the moment map looks awfully like something you've seen before, right? That's the part of these D terms, part of the potential. And so now if you go back to what do you know about symplectic quotients in mechanics, what you do is that you take a pre-image of some regular levels of these moment maps. So that's this. You take all the you take one for each gauge field, and then you quotient out by the remaining gauge symmetry. So this is exactly the spaces we will be working with, and that's what the vacuum manifold of these GLSMs are describing. I should say that the value of the psi matters, and there's a huge story about what is exactly the corresponding quotient for different values of psi. It's not that so roughly the psi controls the size of certain co-cycles in your manifold, and if psi is 0, then generally you end up with a singular quotient with something singular for psi is equal to 0. So if you move to positive psi region, for instance, you're generally resolving all the vanishing cycles in your geometry. And then I will not talk about what happens when they're negative for now. I mean, sometimes it means something deeply quantum, sometimes it's fine, but it's very example based. Okay. All right. So one little trick I need to tell you before I unveil this extension of GLSM is the Legendre transform. I mean, you all know Legendre transform, but I should just say that this is a special Legendre transform where you're not just transforming the fields phi themselves, but instead you write them in this parametrization as something real and imaginary. So you should think of this as some kind of log of the size of the field, and this is a phase. And then we're going to perform a Legendre transformation with respect to these W's. Okay. So you can take your model, if either nonlinear sigma model or GLSM, and perform this Legendre transformation, and then you end up with some new function describing the model. And just like before, we had a Kähler potential. This is called symplectic potential or de Lausanne potential. There's an advantage to do so. I'll hopefully clarify that later. But here I just show you how you do that very concretely, right? Like if you start with this model, you can just perform a quotient and integrate out W's explicitly, and you'll end up with model like so. Okay. Actually skip this. Okay, so now what's the point about this extension? So you know that there's a theorem that if you have Calabi-Yau manifold, it must admit Ricci flat metric. However, as I said, if I construct a GLSM model, rarely this metric I will obtain is Ricci flat. But the statement of the theorem is basically that as I'm moving over the moduli of these of the Kähler parameters, so over these psi's, there's all sorts of metrics in each fiber, but there's always one which is Ricci flat, right? So there should be one for each of the points in the moduli. GLSM just gives us another one. So the logic of this extension I will show you in the last 10 minutes is that we extend this moduli, we extend the base, okay, by extra Fi parameters, and then we solve certain equation which tells us that stuff is indeed Ricci flat, and then we find a one parametric family inside, which will be exactly the image of the original Kähler moduli of the original model. So by this extension, you are able to fix the other parameters and their interdependence, such that you end up with Ricci flat metric, and then map it nicely to the Kähler parameter of the original manifold. All right. So what is this equation I'm talking about? It's called Monge-Ampère equation. It's nothing else than Ricci flatness rewritten in terms of the potential. And this is the equation. It says that the determinant of the Hessian can factorize this into holomorphic and anti-holomorphic part. This is not a form I want to work with, but rather I want it to be rewritten for the symplectic potential for this guy. And then the statement is just that, again, the Hessian of this function is that the determinant of the Hessian must be exponential of the gradient of this potential with some constants. Okay, so if you manage to find those, and if you manage to construct simple potential like so, you end up with something Ricci flat. So in principle, you can start constructing GLSMs and be checking this function. It's a bit ugly, but doable, especially in Mathematica or other programs. Okay, so now a little step back and basically motivation for how we came up with these shadow fields. There's a funny thing that if you start with the scalar potential I showed you at the very beginning, which doesn't give a Ricci flat metric, and you just change this overall power, it is Ricci flat. And then if you start rewriting stuff, so you introduce some auxiliary fields and basically rewrite this using extra field x5, you end up with this model. And then if this is indeed GLSM, then you can just plug it in and you end up with something that looks like a GLSM with extra field, but a wrong sign. So that's your first shadow field you see. And indeed, like you can, yeah.
Sorry, I missed the step, one step back. So you have the K on top, and then you introduce this X5.
Yes.
And so if what you have to do to X5, integrate it out to get the thing on top.
So here, if I just integrated out V2, I would end up with the previous model and gauge fix X5. Sorry, gauge fix X5 and integrate out V2. So I would end up back in the K.
Okay.
And then if I substitute into K GLSM description of that conical, which we have, and do some field redefinition, I end up with this GLSM which has 5 fields instead of 4. The quotient is still conifold, but the sign is wrong in one of the directions. And so you can go back to what you just learned about toric geometry and try to like redo the obtain the picture from it, and you roughly get the following. Sorry for the artistic impression here, but that's the best I can do. So you get those original 4 guys spanning the conifold, and then you get this one guy, the green guy, pointing in the opposite direction. So you see that this is immediately not Calabi-Yau because of the condition I taught you. However, that was not really a necessary condition, it was sufficient condition. So we still find a right quotient, which is Calabi-Yau. Okay. So now so what are the shadow fields? Now you could probably tell me the definition yourself if you followed along. It's just a set of extra directions in the fan which correspond to negative signature fields in your GLSM. Roughly P can be split into normal and shadow fields, and similarly Q can now have part which only touches the original fields and the one which is rotating it to the shadow fields. I should say that in order to have the quotient of the right size, because you don't want to change your variety, you want to end up with the same geometry in the end, you need the same number of gauge fields as shadow fields, so that the quotient in the end has the right dimension. Otherwise, you would end up with something bigger. All right, so for instance, for A1, it turns out that if you want to perform a quotient, you need to add this guy sticking in the opposite direction as well, and this will be a Q matrix. All right, so now main example, I guess, which is understandable in 4 minutes. A1 example. So as I told you, if you add the green arrow, if you add this green arrow pointing in the opposite direction, and you perform a GLSM quotient, you can actually do it pretty explicitly, and you end up with Ricci flat metric for size being 0. However, if you so you get a Ricci flat metric on this in the singular point, which I mean, it's already better than what you get from standard GLSM, but not really very useful. But if you want to resolve, you want to turn on these xi's. And it turns out that if you feed it into Montampere and crunch numbers, you'll never find a solution which is working for resolved place. So it fails. However, it turns out that if you add even more shadow fields, you can find a way around. So if you add 3 shadow fields instead of 1, and they are looking like so. So this double line means that there's 2 shadow fields, and there's one pointing even in the standard direction. Then you can indeed, in this 3-dimensional moduli, you can find one parametric family of resolved metrics on this 2-dimensional Calabi-Yau manifold. Okay, I'm cutting some corners, but I can explain to people if they're interested. Okay, so you see, okay, it's a bit ad hoc at this stage, and it's not that I'm missing some details. It is really ad hoc. You need to add these things in specific direction and play with it a little bit. But there's some class where we just know the answer fully, and that's Einstein-Keller manifolds. So I'll just roughly say that, quickly say that, and I'm done. So Einstein-Keller is not Ricci flat, but it's a class of manifolds where the Ricci is proportional to metric, right? Turns out that in terms of the potential, it means this, that the determinant is equal to this exponential of lambda k, where lambda is some number. And then it turns out that if you, sorry, I should have said it's not Einstein-Keller, but cones over Einstein-Keller. And so now we can construct cone over it and furnish it with this potential, where this ZZ bar is a new coordinate along the cone. And it turns out that if you calculate the Montampere, or the determinant of this, you'll get this right hand side. If you fix this number properly, like so, you'll get Ricci flat metric. Well, and then it turns out that if you take this guy, if the K is already toric, you can see that upon Legendre transforming the potential, the new one, with respect to Z, in the sense I explained before, just in like a size of the Z, you end up with something like this. And if this is toric, which we always assume, you end up with something what has a pure GLSM form. And so you end up with this description. And then we have basically, we found a general symplectic potential for product of any number of CPNs and a canonical line bundle over it, so cone over product of CPNs, which will give you singular Ricci flat metric. So this is that description. And there's also a one which gives you full resolved one. So that looks like this, but there are some extra terms which can be fixed by some linear equation, sorry, by some algebraic equations. So I unfortunately don't have time to explain that, but there is very concrete expression for this symplectic potential. And I will conclude with this. Sorry for rushing a little bit towards the end. I should say that this construction outside of, so for these classes of products of CPNs and cones over them, everything's fixed. For other examples, stuff is a bit ad hoc and it needs some formalization. We have some ideas, but it's not entirely clear. We need more examples. We have some examples where stuff just fails, or we're just, I don't know, failing to be smart enough to find the shadow directions. So there's a lot of work to be done. Of course, the most exciting thing would be to turn on the F terms and give a metric for contact Calabi-Yau, but that's probably outside of the immediate reach. There's a condition I put under the rug, and that is that shadow fields are always having a range to be non-zero, and that's a bit weird. And it would be nice to have a good condition for why is that the case. There is a very peculiar relation to something called positive geometry and canonical forms on polytopes, which I can tell people in private if they're interested. And then Last thing, we checked that the mirror manifolds for some of these examples are indeed the same because we are not changing geometry, so better the mirror side should also not change, but there's some things to be fixed, and I'll end with that. Seems like it's time.
Yeah,
So
that was exactly. Yeah, thank you very much for this very nice talk, for the nice introduction about toric geometry and VLSM. Are there any further questions? We already had covered. Yes, please.
So missing this very last example, we have IDD25 for that solution.
Yes, it's
You do.
yes. So for that very restricted class of examples, there's a fully resolved case. It's a fully resolved metric. So we turned on fairly equivalence terms.
Can you briefly comment about the IDD25 coefficient being positive or negative? You said in one case is the usual resolution, and then in the it's very quantum. What you mean?
No, I was just referring to this Calabio-Landau-Ginzburg correspondence from a long time ago that you can make sense of negative Fi terms despite not really having a geometric meaning to the vacuum manifold. So it's not really something what's important for us. I was just trying to say that at the physics level you can make sense to those classically prohibited regions and give them some Landau-Ginzburg description.
Okay, so since we
Yeah, very small. I don't know if you mentioned, but did you think of including an S field in this? You said you were not going to.
Right. For that, you would really need to include twisted chiral matter fields, and I think, I mean, it's an interesting question. We talked about it, but it seemed like a extra technical complication for already many complications we have, and we didn't go that way. But I think it's technically possible. It's just at 2,2 level, if you add chirals, the gauging is a bit weird, right? Because you need to add other.
Would there be a motivation for you to do that in principle?
I think it's interesting because then you would go beyond Keller class, and you can study generalized Keller, like whole generalized Keller family, which is the most general 2,2 target for in 2D. So I mean, that was ultimately one of the questions we had, but we first wanted to make it work in the simplest examples. But yeah, it's an interesting question.
Okay, thank you very much.